Okay, I hope now my screen is visible. Good. Um, so we start with this our discussion with this paper, which is an old paper by these three guys, Einstein, Podolsky, and Rosen, who raised a very interesting question that can the quantum mechanical description of physical reality be considered complete? And if you go through this paper, they make a very nice set of logical arguments. Uh, that's what we will try to do. When this paper was written, they actually worked in terms of so what they actually considered were like two particles, let's say each having some momentum x1 p1, x2 p2, and they do run a thought experiment, and then they make some conclusions and they conclude that quantum mechanics is not complete. We are going to do the same, but we are going to do it in terms of spins. So instead of two particles, we are going to talk about with some position and momentum are the variables that we'll be talking about are going to be spins. Okay, they're going to be spins. So basically, this EPR, this paper was kind of so Bohm reformulated the whole EPR thing in terms of spins, and that's what we are going to study. But conceptually, they are identical. So whatever arguments or conclusions are being presented in terms of these variables, similar arguments are presented in terms of spins. All right. So let's see what are the arguments that these three people made. So what we have in mind, a pair of particles. Okay, you can call it particle 1 and particle 2. Okay, and they are in a singlet state. So before that, let me tell you that each of these particles can have is basically a spin half particle. Okay, spin half particle, spin half particle. Okay, you can just take two spins or two electrons or whatever you have in mind. Uh, uh, so the way I'm going to argue, or my language is going to be, from the Copenhagen interpretation, not the ensemble one. But of course, you now know in mind now that very well you have the knowledge that when I talk about a particle, it's a spin of a particle, it's an ensemble property, right? Wave function is not the property of a particle. So let's keep that in mind at the back of my mind. And let's move on. So you have these two particles, and these two particles are prepared in a singlet state. So it's a spin singlet state. So as we know from elementary quantum mechanics, the spin singlet state means my total spin is zero, right? So if I have two spin half particles, right, I can have a triplet state. So so I have two spin half particles, let's say they can have S1, S2, some spins. I can also talk about the total spin of the system, right? And the total spin of the system S can take two values, 1 or 0, and the Z component of S can take 1, 0, -1, and this will be only 0, right? So this is called the triplet state, and this is called the singlet state, right? So this we all, I think, know what is triplet and singlet. So we assume that a state Z0 is a singlet state, okay? So that's what is given, and that's basically how you have prepared the system. You have prepared the system in a singlet state. So if you've not received your attendance, it's okay. We'll note down your attendance. Okay, now what's being said is that if I'm preparing my system in a singlet state, a perfect anti-correlation of outcomes when the spins are measured along parallel axis is the first assumption of the EPR argument. So what does it mean? It means that, see, so I can write my singlet state as 1 over square root 2, up spin z, down spin z. This is for particle 1. Let's say particle 2 minus down spin z and up spin z, right? So what does it tell me? It tells me that if I'm going to measure this in spin down, then obviously this is going to be spin up. If this is going, first particle is spin down, then second particle is going to be spin up, right? But you see, I can also, so the singlet state, I can also write it like this. I can also express the same singlet state like this. Why? Because it is rotationally invariant. Okay. So if I have this singlet state 0, 0, which is basically S equal to 0, SZ is equal to 0. Now if I rotate this, okay, if I rotate this state by some angle theta around some axis, this is very simple exercise. You can all do, it just requires some elementary quantum mechanics. If I try to rotate this state, I'm going to get back the same state. So it's a rotationally invariant state. All right. So I can expand this in any form I like. I can expand in terms of in the z basis or the x basis or y basis, or I could just take any arbitrary direction in space. Okay, I just use any arbitrary direction, and then I can always write my singlet state 0, 0 as some 1 by square root 2, let's say, up spin along some direction, let's say a cap. Okay, down spin along certain direction a cap minus down up. Okay, that's why you're saying that a perfect anti-correlation of outcomes when spins are measured along parallel axis. So you are only you are measuring spin 1 along the a cap direction and spin 2 also along the a cap direction. Okay, if you do that, then you are bound to get anti-correlated. So that means you're going to, so if you so let's say the this observer, he or she measures, let's say S1, this observer measures S2, then you're bound to get the product must be -1, right? Because this is going to measure plus and this is going to measure minus. So we are going to call this as EPRA. Okay. So EPRA means a perfect anti-correlation of outcomes. All right. Please ask any questions or anything is not clear. Please feel free to interrupt and ask. Good. So that is EPRA. This is EP. Let's call this EPRA. All right. Now let's talk about the EPR criterion of reality. Okay. So what do they say? That if without in any way disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. Okay, you can go through it once more that so you're not, let's say you don't disturb the system, you don't do anything to the system, okay, but you're still able to predict and with certainty, okay, its value, okay, whatever quantity you're trying to predict the value of some physical quantity. Let's say you can take angular momentum or the position or moment, anything, okay, if without disturbing it, if you can predict it, right? That means there exists an element of physical reality corresponding to the physical quantity. So, for example, if without disturbing, let's say this is my particle 2, if without disturbing the particle 2, if I can measure its spin, okay, without any disturbance. Okay, let's say I can measure its z component as spin, SZ, right? That means there exists an element of physical reality. So that means this SZ is some real physical quantity. Why? Because I'm able to predict it. I'm able to make predictions about this. Okay, this is their criteria for reality. Okay, which kind of sounds fair enough, right? I hope this statement is clear to everyone. Okay, so what we have done EPRA, perfect anti-correlation of outcomes, and we have done EPR, criteria for reality, till now. All right. Okay, good. So then what do they say? Let us assume that since particles 1 and 2 are spatially separated, so that means they are, okay, so what you can even spread this argument to, like they are separated, these particles are now, you prepare these particles, right? You prepare these particles 1 and 2 and 1 and 2 in a singlet state, and then let's say they move apart from each other. Okay, and let's say they move apart in vacuum, perfect vacuum and all that, so that whatever spin state is there, let's say it was a singlet here, it was a singlet spin state, it's going to remain a singlet spin state. Okay, so you can take them here, very far away from each other, so far away that the act of measuring the spin of particle along the z-axis doesn't disturb the particle 2 in any way. So now if my particle 1 and 2 are here, now I measure SZ, okay, for the first particle. Okay, and I made the measurement. So now we are saying that this is not going to disturb the particle 2 in any way. Why? Because particle 2 is very, very far. Even if some light signal has to propagate, we are saying that it is so far that it's going to take some time for the signal to reach from here to here. It's not going to be instantaneous because of relativity, right? The speed of light is finite. Okay. So the act of measuring spin of particle 1 along z-axis doesn't disturb. So just because we have measured this, it has not created any disturbance for particle 2. Okay. Any questions? Similarly, if we measure the spin of particle 1 along x-axis, so I could know instead of z-axis, I could measure the spin along x-axis. Okay. Okay, so Shubhanshu is asking, can you please explain EPR reality? Sure. So the criteria is if without disturbing the system, we can predict with certainty the value of physical quantity, then there exists an element of physical reality corresponding to the uh, physical reality. So, for example, there is some particle that is traveling in space, right? There's some particle traveling in space. Now, let's say, without disturbing, I'm not disturbing the particle, right? I have some initial conditions for the particles. Okay, let's say, even if you think very classically, I have some initial conditions. Okay, and let's say I'm able to predict the motion of the particle at a later time. Okay, at x at time t, p at time. Okay, if I'm able to do that, then that means this particular physical quantity is real. There's an element of reality. Okay, that's what it. So the x and p, they are actually real real variables, real quantities, because I'm able to make predictions about it. No? I'm able to make predictions about it. Yeah. Okay. Right. So that is their thing. So now let's get back to, so what we were doing, we were measuring in particle 1 spin along z-axis, or now we could say we could also measure the spin along x-axis, right? Doesn't matter. Whether you measure it along z-axis or x-axis is up to this person 1 here. And whatever measurement this person is making is not, that measurement is not causing any disturbance here, because light is going to take finite time to travel from here to here. Okay, this is called a locality assumption. Okay, this is locality assumption, that something is happening here, instantaneously something will not happen here, right? So this is our locality. So what we have done so far, EPRA was anti-correlation of outcomes, right? Anti-correlation. Then we studied EPR, the criteria for reality. Then we have EPRB. EPRB is what? Locality. It assumes locality. Like whatever you do, okay. The Schaffner is asking a question. So in the Einstein's argument, the measurement of spin 1 has a physical reality, right? Since it doesn't affect spin of the second particle. That's right. Yes. Mhm. But that's right. But we are more focused on right now what is happening here, because this is the most interesting part, right? That's what people talk about quantum mechanics being so interesting, because they say that, these spins are entangled and all that. So that's what we are going to uh, test and see what happens. Um, okay. All right. So we have studied anti-correlation, we have studied locality and the reality. Reality is a condition. Yeah, this is the criteria for some quantity being real. These are just our uh, some logical steps that we have now. Okay, let's move forward. EPR argue now, by measuring the z-axis spin of particle 1, we can infer the z-axis spin of particle 2 by using EPRA, that is without disturbing the particle 2, right? Why? Because EPRA suggests you that the outcomes are perfectly anti-correlated. Okay, S1, S2 is -1. So just by measuring spin of particle 1, we automatically are able to infer the spin of the z spin. So what you're measuring as Z1. Okay, you're measuring. Okay, and so now, so we automatically know as Z2 is now automatically fixed without evidently disturbing. So without any disturbance on the particle 2, we are able to infer the spin. There exists, therefore, an element of reality, and that comes from my EPR criteria of reality. That was that without disturbing the particle, if we are able to measure, or if we are able to predict, right, without disturbing the particle too, we are able to predict is its spin along the z direction. Right, without measuring 2, we are able to predict the spin of the spin z of the second particle. Okay, that means the spin z of the second particle, it must be real. It should be an element of reality, right? There exists an element of reality. So it's a real quantity, real physical quantity that you are able to predict. Right? Because after the measurement on particle 1, particle 2 is known to be in a state with a definite value of spin along the z-axis. Okay. All right. Now, but by EPRB, the measurement, so EPRB was locality. The measurement on particle 1 could not have caused particle 2 to acquire this property. Right? Because EPRB is telling you about locality. Right? What is telling you that a measurement on particle 1 is not going to affect measurement on particle 2. Right? So, and now we just here we saw that the particle 2, the spin z of particle 2 is an element of reality. It has some physical relevance and we are able to predict it. Okay. Why? Because after measurement 1, the particle 2, it's already fixed. Right? The spin is fixed. Now, the measurement of particle, but we know that the measurement of particle 1 could not have caused particle 2 to acquire this property because particle 2 was not disturbed on the measurement of on 1. So, if particle 2 is known to have the property after the measurement, it must have evidently have possessed it all along, independent of the measurement made on particle 1. Okay. So see, something has happened here. Particle 1, you're making a measurement, and then you're saying that the value at 2, particle spin, the spin z of particle 2 is like automatically decided. Right? But what has happened that nothing has been transmitted from here to here. Right? Because there's no disturbance that has been created on particle. You've not made any measurement of particle. Okay. So that means the spin z of particle 2 must have possessed this property that its spin z is an element of reality. It must always have been the case. Right? Is it clear? This is a subtle point. So let's find. Okay. Yes, yes. Two people have said yes. Okay, very good. Good. Good, good, good. Nice. So the measurement 1, if when performed, permits us to learn something about the z-axis of spin 2. But the fact we learn about exists independent of the measurement. So whether you measure or not, I mean, it must always have been the case. Right? And now you could do exactly the same argument for the x-axis. That you measure the spin along x-axis and without disturbing the particle 2, the spin along x-axis must also have been automatically fixed. Right? So, or you could take y-axis, z-axis, anything. Right? All right. So now we may argue that either one or the other of these instances can be validly made in a given experiment situation, but not both, since we can measure at most one of the two relevant properties. So what it is telling you that we can't measure what it's basically telling you. According to Heisenberg's uncertainty principle, you can only measure either Sx or Sz, right? Because they have certain commutation properties, maybe Sy plus or minus, I don't know, right? Sx and Sg do not commute, right? So you can either know this or you can know this, right? You cannot know both, according to Heisenberg's principle, right? Make sense? Okay. So Einstein and others were aware of this, That, yes. So then they said that, okay, let's try to make our EPR criteria of reality a little bit more restrictive. Okay. So they are saying that one would not arrive at our conclusion if one insisted that two or more physical quantities can be regarded as simultaneous elements of reality only when they can be simultaneously measured or predicted. So that means if we were to say that Sz and Sx can only be, one of them can be an element of reality or not. If two of them have to be real quantities, real measurable quantities, then we should be able to predict both of them simultaneously. Okay, so we could have modified uh, our criteria of reality to this. Okay, but what they are saying is since either one or the other, but not both simultaneously of the quantities can be predicted, that means they are not simultaneously real. So that's what they said. If this is the case that you cannot, measure and predict spin along X and spin along Z simultaneously, only one of them must be a real physical quantity, right? Yeah, because they have, corresponding to quantum mechanics, they have commutation relations. And because of commutation relations, what happens that you can only know one at a time. You can't know about both at a time, right? So then they can be not be simultaneously. Yeah. So, but what is this implying? This is implying that the reality of the two properties of particle 2 depend on the process of measurement carried out on particle 1. Okay, so see what's happening here. So if I measure the spin along SZ1, then this the SZ of 2 becomes real. If I measure the spin along SX, then SX of 2 becomes real. Okay, so the measurement here is determining what is a real physical quantity for particle 2, and which, by the way, note that which doesn't disturb particle 1 in any way. So this has no disturbance, this has no influence from this side. Okay, right? So this particle 2 has no influence from particle 1, but the measurements are determining which of these quantities will be an element of reality, right? So then they come to the conclusion that no reasonable or local definition of reality could be expected to permit this. So this is basically absurd. Whatever is happening is absurd. Okay. So is this clear until now? What were the arguments? Are there any comments on this? Anyone has a comment? Element of reality. Element of reality means, okay, so it's basically if you have an object and you are able to make measurements on it or make predictions about it, right? That means it's real. So, for example, the position of a particle or the height of a building, things like the speed of my car, okay, energy of the electron, stuff like that. Okay, these are things that I can predict, right? I can measure, I can manipulate. These are elements of reality, right? Maybe something which is not be an element of reality, maybe I don't know. The global phase of a wave function, maybe that's not an element of reality. But okay, so these are things that are real, physically measurable quantity. That's what you mean by element of uh, reality. Okay. Any other comments? All right, good. Um, Very good. So finally, what they're saying is, although the operators, um, although the operators for these two observables don't commute, Sx and Sj don't commute, therefore cannot, according to quantum mechanics, possess simultaneous definite values. The x and z axis possess simultaneous definite values because they are element of realities, right? And that's what we have discussed, and that mean that the descriptive limitations imposed by quantum mechanics can be beaten, because you see, without doing anything to the particle 2, I'm able to uh, tell stuff about particle 2. What is the spin of particle 2, right? There's one more question. If you're making measurements of, according to particle 2, those measurements were taken in the past because light takes time, so it takes time to travel to particle 2. That's right. That's right. That it takes time to travel for light to go from particle A to particle but what quantum mechanics is telling you is that, or at least what's being said is that so that is being incorporated, right? That's being incorporated. So if you see here, uh, if you read this, assume that since particle 1 and 2 are spatially separated, okay, the act of measuring spin 1 along z axis doesn't disturb. Okay, this assumption is motivated by relativity's prohibition on causal relation between space-like separated events. So we are in space-like separated events. Okay, so if you know the light cone, right? So we are here. Okay, there are some, let's say if event A has occurred here, we are inside this. Okay, so light, of course, you're right. Light takes some finite time to go, but that has been accounted. So we are not doing the measurement after the light has reached and all that. We are making measurement at different time. No, we are not making measurements on particle two. Remember, we are only making measurements on particle one. We are making measurements on particle one and then trying to infer what is happening to particle two. Right? Because that's what is the prediction. That's what is EPRA. What does EPRA tell you? EPRA, it tells you that S1, S2 is always minus 1. So as soon as my S1 is measured, S2 is fixed. Okay? That's the whole point. S2 is fixed. Right? So we are not making measurements. We are only making measurements on one and trying to tell about the other. All right? Okay. Um, Very good. So what is being finally said is that, so we had EPRA, let me just call it A, that was on anti-correlation of, okay, anti-correlation of the spin. So S1, S2 is equal to minus 1, right? And then we had B. B is what? B is locality principle. That nothing at A affects. So what is happening here doesn't affect what is happening here. Okay. This implies negation. So this symbol is negation. Negation of C. And what is C? The claim that quantum mechanical description of reality can be considered complete. So we went through a series of arguments, and then we showed uh, that the spin of the second particle, okay, whether it's along x-axis or z-axis, they are both elements of reality. Okay. So, which of course is absurd. Um, so the negation of EPRC is the claim that quantum mechanical description of reality can be considered. complete. So what we have done is that we have taken this anti-correlation and this relation that my product of spins must be -1. Okay, and we took locality, and both of these implies it. So A and B implies not C, and C is what that quantum mechanics is complete. Just give me a moment. I think there is something wrong. Okay, I think you can now see my screen, this notepad again. Um, all right. Okay, so A and B imply not C. This is logically equivalent to not A or not B or not C. That means what? That means something is wrong. That means either S1, S2 is equal to -1, either this is wrong, okay, or or locality, or locality is wrong, or quantum mechanics is incomplete. Okay. Now, what's Einstein saying? Given the empirically well verified quantum mechanical expression for certain correlation, the advocate of orthodox quantum theory is forced to relinquish either locality or the completeness claim of EPRC. So, what he's saying is that this EPRA, that okay, that these correlations, that S1 into S2 is equal to -1. Okay, these are empirically well verified. So experimentally, people have seen these in certain experiments. Okay, so that means so A is true. Okay, so A is not false. So either B must be false or C must be false. So either locality, the claim of locality must be taken away, or the claim of completeness must be taken away. So this is what was told by Einstein in the EPR paper. So I hope you got some idea at least at what is being tried, what is being said here. Okay. So it's much more than, people usually talk about spin up, once being spin being up, other being minus. But that's not always, I mean, that it is much more than that. Okay. It's much more than that. Okay. All right. Any further questions or comments? Right. If not, then let's now move to Belgium. So this, so as I mentioned that this paper was in 1935, and then for another, I don't know, few decades, nothing much really happened. And then Bell tried to uh, do some mathematics on it. And so that's called as Bell's inequality. Okay. So EPR is done. Now let's come to Bell's inequality. So let's what Bell's inequality is telling us. So in our minds, we have the same system that we had when we were discussing the EPR. So what we have is you can think of, or you could even do something more general, right? So you have, uh, you're measuring two physical quantities. Okay, you're measuring some physical quantities A and B. For example, you could measure the spins. Okay, so now Right. Okay. You could measure it along x-axis or z-axis or whatever. Now, so that depends on my instrument setting. So A is a function of A. What is this small a bar? The small a bar is my instrument setting. Okay, what does it mean? It means, let's say, if I have a Stern-Gerlach setup, I could either set it to along the z-axis or the x-axis or the y-axis. Okay, that's what it tells you. So that means it tells you what I'm measuring. I can either measure SZ or SX or SY, whatever I want. Okay, so this is the instrument setting. Similarly, the apparatus here at B also has some instrument setting, right? And these are controllable. It's in our hands how we wish to, what we wish to measure, how we wish to measure, right? And lambda denotes some uncontrollable parameters. Also, you can think of them as some hidden variables. Okay, so what we are saying is that whatever A is measuring, let's say A is measuring this quantity A of A bar, comma lambda. Okay, so whatever is being measured by this instrument, it depends on the instrument settings and it depends on some factors we don't know anything about. Okay, there could be lot of other factors, right, that could affect the measurement outcome. Okay, so those are being all, so this lambda incorporates all of those factors, and that's what these parameters which are uncontrollable. So we can't do anything about lambda. Okay, they are just there. Okay, so then A becomes a function of my instrument setting A comma lambda, and B becomes a function of B comma lambda, right? Okay, and now we invoke Einstein's locality. So that means what this is telling me is that A is only a function of A and lambda. It is not a function of B and lambda. Okay, so such type of functions I'm going to exclude. Similarly, anything like B of A comma lambda comma B. So B is only dependent on B. This also I'm going to exclude. Okay, so that means whatever I'm measuring at B, it has some independent settings. I can choose my settings independently. Okay, now it is not being influenced by what the small a is being set here. Okay, so B is only function of B and lambda, not a function of A comma B comma lambda. Similarly, capital A is also only a function of A lambda, not a function of A lambda and B. Okay, yeah. So that's this, the locality principle. And now about lambda, we are not specifying what this lambda is, but we are specifying it has some probability distribution, some rho of lambda, d lambda. Okay. So now what Bell did was he studied correlations. Now, and when you study correlations, where correlations are, again, there are no actually correlations between single particles. You only have to, um, but lambda can be common to A and B. Um, That's right. Lambda can be common to A and B. That's right. But the point is that lambda will only locally act at A and locally act at B. I don't know if that makes sense. Yeah. So it's acting, so lambda is there, which is, so maybe some common source. So there can be some common source, which we're calling lambda, but it's acting on them one by one or individually. Okay. So that's locality basically. Lambda acting here is not going to suddenly do something to the lambda there. Okay, that's what is the point. Okay. Right. So then we have Einstein's locality and we have some probability distribution for lambda. And now we study correlations between. So we are measuring these quantities A of A comma lambda, okay, and B of B comma lambda. And what we are doing is we are measuring something like the correlation C of A comma B is equal to A of A lambda, B of B lambda, rho of lambda, D lambda. Okay, this is the quantity that we are. Okay, there's a comment, people saying everything is connected according to quantum physics is wrong. Uh, this is a very vague statement. Okay, it's not, I wouldn't even call it a very scientific statement. Everything is connected. I mean, yeah, if you think about that way, and everything is connected. But yeah, I wouldn't worry too much about this statement. It's not a very scientific statement, according to me. So this is the correlation that we're trying to measure. Um, Okay. And so what we have integrated over all the hidden variables. So we don't know what the hidden variables are, but let's say there are hidden variables and they affect these measurement outcomes. So we integrate over all of them and then we find some correlation A and B. And again, these correlations, uh, yeah, of course, there are YouTube videos saying all sorts of nonsense and let's not. mm worry too much about these YouTube videos. Okay, so now we're going to put some weaker restrictions on A, the measurement outcomes, the A and B. So earlier I told that the spin, let's say spin 1 and spin 2, I can take either plus 1 or minus 1. But in general, because we have not specified what these A's and B's are, right? We have not really specified whether they are spins or not. There could be some other observables. So A and B, we are just taking them to be some observables which can take some value less than equal to 1 and B is also, mod B is also less than equal to 1. So they are in fact weaker restrictions. Okay. So we are giving some more freedom to what A and B can be. They can be anything between minus 1 and 1. Okay. So this is my correlation and from here I can very easily derive the Bell's inequality. I'll just sketch the proof. So what you have to do is you have to, so C of A comma B, and I take two more instrument sets. So I'm taking in there in total four instrument settings. Okay, A, B, A prime, B prime. A and small a prime are some instrument settings for my particle 1, small b and small b prime of a particle 2. Okay. And so that means, so for example, in context of spin, this could be that I'm measuring spin along the z-axis and b could be along x-axis, a prime could be along x cap plus y cap axis, b cap could, I'm just giving an example, x cap minus y cap. I could choose them whatever I want to be, basically. Doesn't matter. Okay, so now we are having four different instrument setting. We are trying to find some relation. So if I just naively write the equation 1, putting equation 1, what do I get? I get A of A comma lambda, okay, B of B comma lambda minus B of B prime comma lambda times rho of lambda d lambda, right? That is this. Okay, now I'm going to add and subtract. Okay, so A of A comma lambda, B of B comma lambda into 1 plus A plus or minus A of A prime lambda B of B prime lambda rho d lambda minus integration A of A lambda B of B prime lambda, okay, 1 plus or minus A of A prime lambda B of B lambda. rho d lambda. So all I have done is I have added this. So you see I have added this plus or minus a prime lambda b prime lambda, and I have also subtracted the same term. Let's say here I am taking a lambda b lambda common. Here I am taking a lambda b prime lambda. So here I have bb. So this I just added and subtracted the same term. So I've just added and subtracted 0 basically. Okay. So that's what I've done here. And now I can use the triangle inequality. So what is that? So if I have some f of integral of f rho, let's say d lambda, is less than equal to integral of modulus f rho d lambda. Okay, so it's the same thing, is at sum of a plus modulus of the sum of a plus b is less than modulus a plus modulus b. It's the same thing now, just written as an integral. Okay, that's what it is. Okay, so I can apply this and then I get mod c a comma b minus c a comma b prime is less than equal to. So now, so I earlier, if I want to put a mod, I'll have to put a mod outside, mod of the whole thing. But now with triangular inequality, I can put mod inside the integral, right? So it'll be less than equal to integral a lambda b lambda times 1 plus or minus a prime lambda b prime lambda rho of lambda d lambda plus integral a of a lambda b of b prime lambda modulus of 1 plus a of a prime lambda b of b comma lambda rho d lambda. Okay, this is just straightforward math. And I know that my A and B have some upper bound. So mod A and mod B are less than equal to 1. Okay. So I can write that this thing must be less than equal to, okay, 2. Okay. 2 plus integral. Okay, let me just write this properly. So it must be less than equal to 1 plus or minus A of A prime lambda b of b prime lambda rho plus integral of 1 plus or minus a of a prime lambda b of b comma lambda rho. Okay, good. And why is that? That is because this thing. So I had this product of a and b, right? So that must be less than 1 because both a and b are less than 1. Okay, so now I have this thing that so you see I have this quantity 1 plus or minus in both of these integrands. I have this quantity, so we can just take one of them. Let's say a prime lambda b of b comma and modulus of that. Now you see this particular quantity here, the question, can you please go over the integral again? Okay, sure. So what I've done is I have taken from here, I've added plus and minus this, and then I've used the triangular inequality. Okay, and then I get mod C AB minus mod C AB prime is less than equal to. So what I have done here, so I had inside this guy into this guy, right? And that with the triangular inequality, I put the mod inside the integral. So I get this into this, mod of this into mod of that. okay, plus mod of this into mod of this, right? And I know that uh, mod of A into B must be less than 1. So see, then this becomes less than equal to 1. This guy also becomes less than equal to 1. So then what do I get? I get 1 plus or minus, okay, this term, second term here, plus 1 plus or minus the second term. Okay, that's what I've done. So let me now see this one of these terms. They are of the same form. So 1 plus or minus A into B. So I know A into B, it lies between, let me call this X. So let lies between minus 1 and 1. So modulus 1 plus or minus X, if an X lies between minus 1 and 1, okay, I can always write this as 1 plus or minus X. Yeah, because this quantity is itself is between minus 1 and 1. So if I'm going to add 1 to this, also, then it's going to be always between 0. So this quantity is between minus 1 and 1. So if I add, so let's say if I add 1, okay, and if its X is between minus 1 and 1, so that means modulus of this is also equal to this, right? Yeah, I hope this is clear. Okay, I can also send you this later, the sketch of the derivation. So then, so what I'm trying to do in the end, so I'll get this. So I'll get 1 plus A of A prime lambda, B of B prime lambda, rho D lambda, plus um yeah, plus this was there was a minus sign here. Okay. Um, plus the other thing. A prime lambda B of B comma lambda rho D lambda. Okay. So from here, and what do I get? So what we had started with C of A comma B minus C of A comma B prime. Okay. So we showed that this is less than equal to 2 plus or minus C of A prime comma B prime plus C of A prime comma B. So A prime comma B. Okay. Okay. So now we can take so it is less than 2 plus this or 2 minus this. So we can take the stricter of the bounds. Right. So for example, so what we can say that C of A comma B minus C of A comma B prime modulus is less than equal to minimum of 2 plus S, 2 minus S. Where S is S, this thing I'm calling as S. This whole thing I'm calling as S. Right? So it is less than both 2 plus S and 2 minus S. So then of course it has to be less than the minimum of both. No? So that means, but what is the minimum of 2 plus S and 2 minus S? It's 2 minus modulus of S. Okay. So then I can then very simply write mod of C of A comma B minus C of A comma B prime plus modulus of C of A prime comma B prime plus C of A prime comma B is less than equal to 2. Okay. This is a form of actually Bell's inequality. Okay, what you'll see in the paper will is like a slightly different version, but it's the same thing. Okay, so what Bell was the point of this is that you can use the principle of locality to derive this particular inequality. Okay. And so, as I mentioned, that this inequality can also be made stronger if we talk about the probabilities of outcome. So, what you'll probably see in the Bell's paper, he doesn't talk about this outcomes A and B, he talks about the probabilities of outcomes. Okay. Okay. And then he uses the same principle of locality, that row of 1, 2. Okay. So what is so row of 1, 2 is basically the probability that one part, that A and B are my instrument setting, lambda is my hidden variable, and I'm measuring. So it's a joint probability distribution basically, right, for both of them, and that can be separated. It can be written as row 1 into row 2. Okay, and that's the same thing that we also used here. We invoked Einstein's locality in this form. So if you see here, what we had done is we had not considered any functions like that. Okay, so if here we had a joint probability distribution, it would be, something like A, B, lambda, okay, some joint probability distribution, and that is just some A of A comma lambda, or B of B. Not it's here. It's not a probability. It's basically what they're trying to measure some correlation. But what the point I'm trying to say is that this row 1 2, which is this joint probability distribution, right? That basically row 1 2, that something is being measured. Okay, you can call that quantity X. Okay, and with some instrument setting. Okay, this is for, let's say, A, and then for the instruments, then something else is being measured over there with some instrument setting, that this can be exactly factored as row of X comma A, row of X comma lambda, X comma B comma lambda. So even if there are these hidden variables, lambda, they are acting locally. Okay, they're acting locally at both A and B. And with this, you can derive the Bell's inequality. Okay. Um, right. So that's the Bell's inequality. So what Bell's inequality tells you, it gives you that if you're making some measurements on some correlations, okay, then those correlations, then the principle of locality would imply that your correlations, whatever you're measuring, should satisfy this inequality. Okay, so for example, let's take a simple case. Let's say if I'm measuring, let's say I'm measuring my singlet state. Let's come back to the singlet state. Okay, so what was my state? My state was psi 0. Okay, and psi 0 is, we can expand it in my z basis as a up down minus down up by root 2. Right, this was my singlet state. Now what we could do is we could right, so we have to take 4 different instrument settings. Let's say A cap prime, B cap B, and B cap prime. So what are these instrument settings? So what are we trying to measure? We're trying to measure the spin. Okay, so the thing that we're trying to measure here is basically sigma dot A cap, and B is measuring sigma dot B cap, or A prime or B prime, whatever. We're trying to measure spins along different directions. Okay, along A prime, B prime. All right. And the most important thing is that we are measuring these correlations. So measuring the expectation values here. not single particle measurements. Okay, so this is what we are trying to calculate. This will be our correlation A comma B in this case, right? That you're trying to measure the spin along the A axis for particle 1 and the spin along the B axis, B cap axis for particle 2, right? And now you can very easily, if it is a singlet state, you can very easily prove that psi naught A cos B psi naught is actually minus cosine theta AB. You can very easily prove that. Where what is theta AB? Theta AB is the angle between the A axis and the B axis. Let's say this is A cap axis, this is B cap axis, this is my theta. Okay, this is true for the singlet state, mind you. I'm only talking about the singlet state here. It's a specific type of state. Okay, and this is what quantum mechanics tells you, that this should be my outcome, right? So now one can take some very specific values. One can take A cap as x hat, okay, B cap as x hat plus y hat by square root 2. Okay, B cap hat is 1 by root 2 minus x hat plus y. I'm just using some directions. A cap hat is equal to y. A cap hat prime is equal to y prime. So what is happening is that, so I have some singlet source, and spin 1 is going towards, uh, 1 is being measured somewhere, spin the second particle is being measured somewhere. And so let's say this is x and y. So what is A measuring? A is measuring along this axis. Let's say it measures along this axis for some of the particles, and it measures along this axis. Okay, so you have an ensemble of particles, and so X is making two measures, not on the same particle, on the same, from the same ensemble of particles you are making measurements. So first you measure for some of them Sx and then S1. What about B? B is measuring for along this direction, this and this direction, B cap prime direction. Okay. So then very easily one can calculate, and I know the prediction is, this is my prediction. I very easily know. And this I can calculate. Very easily I can calculate. We just have to use some elementary matrix multiplication and all. C of A comma B, you can now calculate. It's going to be minus cosine of the angle between A and B. So, okay. Angle between A and B is 45. So this is going to be minus 1 over root. Okay. Similarly, you can easily calculate A B prime comes out to be 1 by root 2 C of A prime B prime is equal to minus 1 by root 2 C of A prime B is equal to minus 1 over root 2. Okay. Now let us put all of these in the inequality. So inequality is this equation 2 here. Okay. So what's the inequality saying? That modulus of CAB minus modulus of CAB prime. So this minus the modulus of minus 1 by root 2 minus 1 over root 2. Okay. Plus modulus of the other two, sum of other two, minus 1 over root 2 plus minus 1 over root 2. Okay. This is the answer is 2 times root 2. But, and we know that this is greater than, not equal to, greater than 2. But if the inequality had to be satisfied, then this thing here, it must be less than 2. It could not have been greater than 2. So the inequality is being violated. Okay. So Bell's inequality is violated. wealth inequality is violated. Okay, and this comes from just doing your very standard elementary quantum mechanics. Okay, but what have we assumed? All we have assumed is basically we have assumed that okay, there can be hidden variables, but as long as those hidden variables are acting locally, okay, then my Bell's inequality must be satisfied. But what I'm finding my Bell's inequality not being satisfied. Okay, so the violation of Bell's inequality is something that is being theoretically protected. Now, even in the experimental side, I mean, that's what the people got the Nobel Prize for. They have seen signatures of the violation of Bell's inequality, but they don't do measurements with spins. They do measurements with photons, like photon polarization and all that. Okay, so I won't have time to discuss all that, and I don't know those topics very well myself, but that's the idea that they have done experiments with photons and they have seen that Bell's inequality is being violated in all these quantum experiments. So, so what does that tell you then? So you have heard me speak for more than an hour. So what would you conclude if I were to ask you the question that okay, we learned about EPR and we also learned about Bell's inequality, and we saw that Bell's inequality it can be if you assume locality, then Bell's inequality must be true. And quantum mechanics is showing that Bell's inequality should not be satisfied when we are trying to measure these correlations, okay, of these entangled, quote unquote, entangled particles or entangled spins. Okay, so what do you infer? You can maybe type on the chat box. What do you understand from all this? Quantum mechanics, okay, quantum mechanics is right. Well, okay, let's also hear others, and we can have a discussion. No one else has understood. If you've not understood anything, it's totally fine because it's okay. No one it's understands anyway what's happening in quantum mechanics. So um, at least if you have some thought on it, please you can even speak up if you like. No one has anything to say. That's bit disappointing. Well, the inequality shouldn't be satisfied for quantum mechanics. Right, that's what we saw. The local assumption is not true. Yeah, we could say that the locality principle must be kind of re-examined. Mm-hmm. Anything else you want to say? Okay, think about it. It's of course not, there's no yes and no answer to these questions that something is right or something not right. It's something that you also can think. But that's right. So Bell's inequality, one thing which it did was it kind of ruled out local hidden variables. Okay, so local hidden variables are not required because that's what Bell's inequality, to me, that's what it has done. Now the reason that why we went over, why we decided that we're going to introduce it, that now what you are already, working on a
Base inequality.
quantum. Sorry, what? Did you say something?
ಏ ಗೇಮ್ ಆಡ್ತನವ ಗೇಮ್ ಆಡ್ತನವ
request you to please mute whoever is speaking. Okay. Um, so what I was saying, I forgot. So right, so why we decided to go over this is because now you're running these things on a quantum computer, right? And now you can, design a Bell state, right? You can take a 2-qubit Bell state, and you can actually try and see whether this inequality, okay, inequality is just correlation, right? You are just measuring things. Okay, all you have to do is you have to just measure this here. So don't forget about this row of lambda and all that. You can just measure the spins, okay, along 4 different directions here, like we have done here. Um, this here, right? This one. Okay, you just make measurements and you see whether you can see for yourself whether this equality is being satisfied or it's not being satisfied when you do these things on your quantum computer. I think that would be really very interesting to see. Okay, and another thing that you must keep in mind is that we're talking here about correlations, not of single particle measurements. Okay, so in my discussion, I was speaking it as particle one, particle two, but you must keep in mind that these are ensembles, and we can only all of these inequality. It's only true for the case of ensembles. Okay, not for single particle measurements. Okay. All right. So I think with that, I have finished what I wanted to say. So do you guys have any other final questions or comments? Please, I'll just wait for 1 minute. Okay, if there are no further questions, we've already short time. So we are going to meet at 5 o'clock. Okay, because 4:25 almost. So let's meet or let's go. Okay, so Shubhanshu is has asked a question. EPR reality thing is actually not valid thing in this case. So basically, if you ask me the way APR, what they were first thing, what they really attacked was to me the Copenhagen interpretation that particle one is simultaneously doing something to particle two. So that was being attacked. So that further gives you a reason to think in terms of ensembles when you're talking about quantum mechanics and not two single particles entangled. Second thing is that the idea of locality again. So they had this assumption about locality which needs to be re-examined. So Rihan, can you please mute yourself if you're not? Okay. All right. So I think I hope at least you got something out of the lecture. And you can also ask questions later. You can go back, think, and ask questions. So we'll stop now, and we're going to meet at 5 o'clock. See you.